Hello. In this lecture I will be explaining the basics of logic operators, Boolean algebra and truth tables. I will show you that logic is not only about flow control, but that logic can actually help you to solve problems. And as always, do not hesitate to pause the video if you need to think about stuff or look what's happening. Programmers work with logic all the time. Still, many programmers never learned any formal logic, but they use it anyway. If you put some time in understanding formal logic, you will realize that it can be used for much more than programming flow control. Logic, in fact, is a powerful tool for solving problems. So let's start with operators. In general, an operator is a thing that operates on another thing, or things. We all know operators like plus, minus, and times, and divide, and that we can use them to model numerical problems. Well, in mathematical logic, we use operators to model logical problems. They operate on values that represent validity, true or false. Now, of course, there are various types of logic. In fuzzy logic, you don't have such a tight boundary between true and false. But we are looking at one particular type of logic here that only uses the values true and false. It is easiest to demonstrate this in an example. So, consider the following statement. Outside office hours, Jane plays video games. The statement is based on the validity of two things that can be mapped to variables. The first variable, A, it is outside office hours. The second variable, B, Jane plays video games. The variables A and B can each be true or false. If A is true, it means that it is outside office hours. If A is false, it means it is in office hours. If B is true, it means Jane plays video games, and B is false, means that Jane does not play video games. A and B can only be true or false. This means there is nothing in between. Either it's office hours or not, and either Jane is playing or not. This brings us to our first operator. The statement expresses an implied relation from A to B. The formal notation of this is as follows. We use an arrow to indicate that A implies B. The arrow is called the conditional operator. A implies B can be read as, well, that A implies B, or if A, then B. A implies B tells us that outside office hours, Jane plays video games. If we want to express more ideas, we need more operators. For instance, if we want to negate an idea, we can use the exclamation mark, the not, the negation operator. Not A, it is not outside office hours. And not B means Jane is not playing video games. Given the above, what can we say if Jane is not playing video games? Every conditional statement has a contrapositive statement. Because it being outside office hours forces Jane to play video games, if she is not playing, it cannot be outside office hours. So, not B implies not A. Think about it if this is unclear. For any two variables A and B, if A implies B, then not B implies not A. So A implies B is equivalent to not B implies not A. Without good understanding of formal logic, it is very easy to fall in a classical trap, and that is called the inverse error. What can we say about Jane if it is in office hours? Think about it. Nothing at all. A implies B only tells us something about B based on A, and nothing about B based on not A. If it is inside office hours, we simply cannot tell if Jane is playing or not. If we want to convey the idea that Jane only plays games outside office hours, we need another operator. If we want to convey the idea that Jane only plays games outside office hours, we need another operator. And that is A is equivalent to B, or the operator is written down as a double arrow, double directional arrow. This symbol is the biconditional operator. A is equivalent to B should be read as if and only if it is outside office hours, Jane plays video games. A is equivalent to B tells us that A implies B, but also that B implies A, and consequently that not B implies not A, and not A implies not B. Knowing about A tells us something about B and vice versa. In this case, it means that A and B are equivalent. This brings us to some well-known logical operators. We have the AND operator, the OR operator, and the exclusive OR operator. The AND, OR, and exclusive OR operators are well known because they are included in most programming languages, so you may well have seen them before. So let's have a look at them one by one. AND expresses the idea that all ideas are true. A and B is true if A is true and B is true. A and B is analogous to the intersection in set theory. OR expresses the idea that any idea is true. A or B is true if either A is true or B is true, or both are true. A or B is analogous to the union in set theory. The exclusive OR expresses the idea that one and only one idea is true. In other words, if one idea is true, the other must be false. For A exclusive OR B to be true, A or B must be true, but at the same time A and B must be false. A exclusive OR B is analogous to the symmetric difference or the disjunctive union in set theory. I've written both symbols for that behind it. Here is a simple verbal example of these operators in action. A. You ate Chinese food. B. You ate Indian food. A or B means that you ate. A and B means you ate and you mixed your dishes. A exclusive OR B means you ate, but you didn't mix any dishes. Make sure you have a good understanding of all the operators we have discussed so far. Here is a table showing all combinations for two variables. Now take your time studying this table. Note how A implies B is equivalent with not A or B, and how A exclusive or B is equivalent with not A is equivalent with B. This type of table is called a truth table, and they can be very valuable tools for solving problems. So please go ahead, pause the video and study this table. Truth tables can be of great help unraveling logic riddles. You just need to figure out the logical variables and list all true-false values of the expressions you identified in the riddle. Let's have a closer look at truth tables. If we have a variable a, we can reflect all possible values of a in a truth table. Like this. The green T stands for true and the red F for false. If we want to reflect all combinations of two variables, the size of the table will sort of double. Like this. In general, if you have n variables and you lay them out in a column each, the table will have n times 2 to the power n rows. This gets big very fast. So you will have to carefully choose the variables and expressions that you want to reflect in a truth table, in order for the table to reveal the solution you are seeking. In the end, truth tables are not enough. We need to be able to work with logic mathematically as well, if we want to create efficient models of the problems we need to solve. Just as with numerical problems, we need algebraic rules for manipulating and simplifying expressions. The branch of algebra that deals with mathematical logic is called boolean algebra, and that is named after George Boole, who introduced it. Now, we are going to have a look at the most common rules of boolean algebra. Take your time to study each of them. Use truth tables to make things clear if they are not. And you will see that truth tables are really, really nice to have. First is the rule of associativity. A and B and C equals A and B and C. Likewise, A or B or C equals A or B or C. Distributivity. A and B or C is equivalent to A and B or A and C. A or B and C is equivalent to A or B and A or C. Again, just write down the truth tables for them if you don't immediately find this logical. Now, this law, de Morgan's law, is a very, very important one, and you will sometimes, even without knowing, use it in programming, because it tends to make your code more readable. But okay, de Morgan's law is as follows. Not A and B is equivalent to not A or not B. Not A and not B is not A or B. I'm trying to say it as it is written, but you get the drift. You see what's written there. These rules will help you to make your code clearer, but also to solve problems, as we will see. Let's have a look at Boolean algebra in action. Consider the following problem. Work is stopped if it gets too hot, while the air conditioning is off. Work also stops if it gets too hot and the blinds do not work. What is the condition for work to be done? First, we are going to solve this using Boolean algebra, and after that we solve the same problem using a truth table. If you model the problem using logical variables, you can express the various conditions using algebra. First we identify the variables. A, it gets too hot. B, the air conditioning is off. C, the blinds are not working. And D, work is stopped. From the text we can write A and B or A and C implies D. Let's go through this. Work is stopped if it gets too hot while the air conditioning is off. That is A, it gets too hot, and B, the air conditioning is off. A and B implies that work is stopped. Or work also stops, that's the or, if it gets too hot and the blinds do not work. A, if it gets too hot, and C, the blinds are not working. So A and B or A and C implies D. Using distributivity, we can simplify this too. A and B or C implies D. We want to know the contrapositive. We want to know when work is done. That means what we want to know is not D. Well, the contrapositive is not D implies not A and B or C. So let's apply De Morgan's law on this, and we will get not D implies not A or not B or C. Just check back with the previous definitions and you will see that this is correct. And also with truth tables. Now this can be further simplified by applying De Morgan's law again. And then we get not D implies not A or not B and not C. The conclusion is that work is done when it is not getting too hot or the air conditioning is on and the blinds work. And that is exactly what it says here. Not D, that means work is done. If not A, if it is not too hot, or if the air conditioning is on, not B, and the blinds are working, not C. So now I've seen that by just doing a bit of algebra, we simply solved a logical riddle. Now we're going to do the same thing using a truth table. Let's first find the relevant expressions for A, B, C, and D. We already did that using algebra, but now we want relevant columns for our truth table. First, A and B. 2, A and C. Third, 1 or 2. And fourth, 3 implies D. Now this is exactly what the text is saying. Work is stopped if it gets too hot while the air conditioning is off. A, it gets too hot, and B, the air conditioning is off. And we call A and B 1. A and C is work is stopped. Also stops if it gets too hot. So A, it gets too hot, and the blinds do not work, which is C. So A and C, we call that 2. Now 1 or 2 we call 3, and 3 implies D. So 3 implies that work is stopped. Okay. You see, I always copy things that we want to carry on to the next page in these gray areas here. So it's always up here. So now we can start with the table. Here are all the possible combinations of A, B, and C. Now let's add a result for 1 and 2 to the table. You can follow the rules A and B, A and C to find A and B, A and C to see that A and B here is true. A and C is true. A and B is true. A and C in this case is false, so we write a false here. And so on for all the combinations. The next step is to add the results for 3. And just as with the other examples, just follow the rules and you fill out the values for 3. The last step follows from that 4 is that 3 implies D. Now, not D implies not 3. So now we add a not D column, and that one will show us the solution of the riddle. We can clearly see that work is done when it gets too hot, A, only if the air conditioning is on and the blinds work. So here, work is done, and that only happens if A is true, and B and C are false. So that means that the air conditioner is on and the blinds are working. That is the only solution for work being done when it's actually getting too hot. Of course, all the other truth here, all the other situations where work is done, requires that it is not too hot. And those are the columns here, all the values here. Okay, truth tables are hard to talk about like this, but they are very visual, and please study them and you will see how valuable they are. So you have now seen that for yourself, that logic provides you with powerful tools for solving problems. I fully understand that if this is the first time you see formal logic, it can all look a bit abstract and complicated. My recommendation is that you take the time needed with the algebra and create truth tables to see how it all fits together. Especially just go out on the internet and Google logic riddles or puzzles and try to solve them using the truth table. The one advantage is that at least it is all perfectly logical. Okay, that's it for this lecture. I hope you enjoyed it. In the next lecture, we'll start looking at discrete mathematics. Well, to be fair, logic is also discrete mathematics, but we're going to take a look at how we can count in the right way. So see you then. Bye-bye.